Usually, when we talk about software or artificial intelligence or cloud computing, we project this expectation of a completely frictionless digital utopia.
Right, entirely weightless.
Exactly.
Yeah.
You write the code, the data floats up into the ether to a server somewhere, and the algorithm just instantly, silently solves your problem.
Yeah.
We think of technology as clean and perfectly ordered.
It's a very seductive illusion. We love the idea of the digital world precisely because it doesn't have gravity. It doesn't have grease, it doesn't have friction, and it certainly doesn't have violently moving parts.
But then you take that beautifully clean, pristine software, and you try to drop it onto the factory floor of a traditional textile mill. And suddenly, your frictionless digital dream hits a massive, unforgiving brick wall.
Oh, completely. It shatters.
Because we are looking at an industrial landscape that is chaotic, heavy, and operating at a speed that is genuinely difficult for the human brain to even process.
It is the absolute definition of a physical bottleneck. What we are exploring today is the violent collision between pristine digital logic and the brutal, messy physics of real-world manufacturing.
Yeah, and if you are that person who is endlessly curious about how the world actually works, how the things we touch, use, and wear every single day are pulled into existence, you are in exactly the right place.
Absolutely.
Today's deep dive is going to completely change how you look at the shirt on your back. Our mission is to cut right through the corporate buzzwords, the tech bro jargon, and the empty hype. We are going to explore the hidden high-tech revolution happening right now inside traditional textile manufacturing.
And it is a revolution in the truest sense of the word. We are looking at how ancient, fundamental human crafts, weaving, dyeing, spinning yarn, are colliding with Industry 4.0 technologies. We are talking about the integration of localized artificial intelligence, cryptographic ledgers like blockchain, and highly advanced computer-aided design.
We're exploring how these tools are, fundamentally redefining global competitiveness. And we're going to be looking at this primarily through the lens of India's rapidly modernizing textile market, which is undergoing an absolutely massive transformation to stay ahead on the global stage.
It's a huge shift, and the sources we have for this are just incredible.
They really are. I was reading this incredibly blunt, founder-grade engineering manifesto recently titled The Quiet Architect. And it completely shattered my illusions about how tech companies understand, or, well, rather, misunderstand the factory floor.
Right, the disconnect is huge.
Yeah. And we're also weaving in findings from a rigorous academic study out of the International Journal on Science and Technology, the IJSAT, which spent time on the ground studying the deep-seated fears and technology adoption behaviors of garment makers in Ludhiana. Plus, we've got some of the latest industry reports detailing the shift towards smart factories.
It's a perfect mix of high-level theory, raw engineering physics, and the psychological reality of the human beings actually doing the work.
So here's the core tension to keep in your mind as we start. We all wear clothes every single day, but we almost never think about the relentless, high-speed physics of how they are actually made.
Most people have no idea.
Right. Right now, the fabric of the shirt you are wearing was likely woven under the watchful, sub-100 millisecond gaze of an edge AI camera designed in a simulated physics engine and tracked by an unchangeable digital ledger.
It is an invisible architecture surrounding an everyday object. But to truly understand how AI is revolutionizing this multi-billion-dollar industry, we first have to understand the physical reality of the factory floor. We have to understand the exact mechanisms of why standard off-the-shelf tech solutions completely fail when you put them inside a textile mill.
Okay, so let's unpack this. Let's step onto the floor. In the Quiet Architect Manifesto, the author paints this incredibly stressful, visceral picture of modern power looms in India. We are talking about massive structures of heavy iron-pushing fabric at terrifying speeds.
Up to 200 meters per minute?
200 meters a minute. I was trying to visualize the physics of that before we started. That is more than 3 meters of fabric moving past a fixed point every single second.
Yeah, it's staggering.
It isn't a piece of cloth you can look at that point. It is just a blur of raw tension, vibrating threads, and deafening mechanical noise.
And that speed is the root of the baseline problem the author outlines. Historically, and even in many massive facilities today, human inspectors are the ones auditing this fabric.
Wait, humans?
Yes, humans. They are standing at the end of the loom trying to watch this highly textured, tension-varied fabric flying past them for a 10-hour shift.
Which seems biologically impossible. You are asking a human eye to stare at a blur of crisscrossing threads moving at 3 meters a second and spot a microscopic broken thread. Or a tiny drop of machine oil that might be, what, half a millimeter wide?
It is entirely beyond our physiological limits. The human eye relies on saccades, these rapid, jerky movements, to fixate on objects and build a visual map. When the object is moving at 3 meters a second, the eye simply cannot track it smoothly while simultaneously maintaining microscopic focus. The brain tries to compensate, and the result is what the text refers to as optical fatigue.
Optical fatigue.
Exactly. It's an extreme form of cognitive and biological exhaustion. Because of this biological limit, manual inspection achieves only about 60 to 70% accuracy under the best conditions.
Which means they're missing up to 30% of the defects. The piece specifically mentions things like neps, which, for those who don't know, are these little tangled knots of fiber that happen during the spinning process, broken ends, or subtle misweaves where the tension just slightly gives out.
And the cost of that optical fatigue is staggering. Missing those microscopic defects results in an overall 8 to 12% defect rate for the factory.
That's a huge margin of error.
It is. In the global fast fashion market, where margins are notoriously razor-thin and contracts are lost over fractions of a cent, bleeding 12% of your potential revenue to scrap fabric isn't just an inefficiency, it is an existential threat.
It's a massive financial bleed that compounds every single minute that loom is running.
Every single minute.
Okay, but I have to ask, if human biology physically cannot see the defects at that speed, why doesn't the factory just use the AI we hear about everywhere else?
The cloud AI.
Yeah. Everyone has an AI startup now that analyzes images in the cloud. We use facial recognition to unlock our phones. We use cloud AI to sort our photos. Why not just point a high-speed camera at the loom, connect it to Wi-Fi, and send the video feed up to an AWS server to spot the neps?
Because that doesn't work.
I mean, to me, it sounds like trying to referee a live high-speed ping-pong match using a video feed that has a 5-second delay. You'd be blowing the whistle for a fault after the players have already moved on to the next serve.
That ping-pong analogy captures the absurdity perfectly, and it is exactly what the author of The Quiet Architect calls the physics wall.
The physics wall.
Right. The tech industry's default reflex answer to every problem is, just send the data to the cloud. But the cloud is entirely fundamentally useless on a high-speed factory floor.
Is that just because of bandwidth? Like the internet speed in a factory is bad?
It's worse than that. It's the literal laws of physics specifically, latency.
Okay.
Even with a massive fiber optic pipe, you are dealing with the round-trip travel time of the data. Let's break down the mechanics here. A standard cloud AI setup takes roughly 500 milliseconds, half a second, to capture a high-resolution image, compress it, send it to a server hundreds of miles away, unpack it, process it through the neural network, package the answer, and send the signal back to the machine to stop the loom.
Half a second, which to you and me sitting at a laptop waiting for a web page to load feels instantaneous.
Sure, but we aren't sitting at a laptop. We are on a loom moving at 200 meters a minute.
Oh, wow.
In that 500 milliseconds of latency, 1.5 meters of defective fabric has already rolled off the line.
Jeez. So the machine has already woven another 1.5 meters of scrap before the AI signal even arrives to say, hey, there's a broken thread.
Exactly. The latency itself actively generates waste, and that's assuming a perfect, uninterrupted internet connection.
Which doesn't exist in a factory.
As the manifesto bluntly points out, factory internet drops. The routers get covered in cotton dust. The power grid fluctuates. If your quality control relies on reaching a server in California and a router resets in Louisiana, your entire production line either halts or it runs blind and produces thousands of dollars of scrap.
Wow. So the cloud delusion is a real physical barrier. You literally cannot fix a physical manufacturing problem with cloud-based software because the time it takes the data to travel is longer than the time it takes the machine to ruin the product.
Yes, physics wins every time.
So what is the actual mechanical solution here?
The actual control point, the only way to beat the physics wall is edge computing. Engineers who actually understand the reality of the factory floor are abandoning the cloud entirely.
Just bypassing it completely.
Yes. Instead, they're taking lightweight, highly compressed AI models and mounting the physical computing power directly onto the machinery.
The sources mention a very specific hardware and software setup for this, something called YOLOV 11 running on NVIDIA Jetson or in Nanos.
Yes, that's the current gold standard.
So instead of waiting for a brain in a faraway data center to tell the loom what to do, this setup essentially gives the machine its own localized reflexes.
That's a brilliant way to phrase it. Yes, it is giving the legacy iron a localized brainstem. To understand how they do this, we have to look at a process called quantization.
Walk me through that. How do you fit a massive AI onto a tiny machine?
Think about a standard massive AI model sitting in a data center. It does its math using 32-bit floating point numbers.
Which is very precise.
Extremely precise. It calculates probabilities to a dozen decimal places. It's incredibly accurate, but it requires massive servers, huge cooling fans, and tons of electricity to run those calculations.
And you obviously can't bolt a server rack onto a vibrating loom.
Right. So engineers use quantization. They compress the AI model by dropping the mathematical precision down to 8-bit integers.
Oh, interesting.
It's like taking an incredibly complex mathematical equation and rounding off the decimals. You lose a microscopic fraction of accuracy, but you gain an exponential explosion in processing speed.
Okay, so you shrank the math.
Exactly. And once the math is shrunk, you can run the AI on an NVIDIA Jetson Nano. Think of the Nano as a highly ruggedized, incredibly powerful supercomputer shrunk down to the size of a credit card.
That's wild.
It's bolted right onto the vibrating metal of the loom. And YOLO, which stands for You Only Look Once, is a specific architecture of neural network optimized purely for extreme speed.
Hence the name.
Right. It processes the entire image in a single pass. The AI doesn't talk to a server over the internet. It doesn't ask permission. It only talks to the motor of the loom.
So it is completely 100% self-contained. The brain and the eyes are physically attached to the machine.
Yes. And this brings us to one of the most critical principles outlined in the Quiet Architect Physics over Software. The author points out that even with the fastest edge AI in the world, generalized, off-the-shelf computer vision models absolutely hallucinate and break down when you show them textiles.
Wait, really? Why? I mean, a picture is a picture, isn't it?
I mean, a picture is a picture, isn't it?
Not at this level of detail. Think about the twill diagonal on a pair of raw denim jeans, or the way a synthetic, shiny polyester thread reflects fluorescent factory lights.
Okay, yeah, that makes sense.
To a generic AI that was trained on pictures of stop signs and cats, the natural, healthy tension of a complex fabric weave looks like a chaotic mess of defects. It will throw thousands of false positives.
Oh, because it doesn't know what a healthy weave looks like. So how do you fix that? Do you just write better code? Train it on more pictures of jeans?
You can't code your way out of terrible physics. If the photons hitting the camera lens are garbage, the neural network is useless.
Garbage in, garbage out. Precisely. You are just processing bad data faster. So instead of writing more code, they fix the physics. They deploy specialized multispectral LED lighting directly over the fabric.
Okay, I love a good visual mechanism. How does multispectral lighting actually help the AI see a defect better than a normal camera flash?
Think of the multispectral light like a topographic map.
Okay.
When you look at a normal photograph of a mountain, the shadows and colors can trick your eye. But a topographic map strips away the color of the trees and the rocks and only looks at the elevation data.
Right, you just see the shapes.
Multispectral lighting does something similar. It blasts the fabric with specific wavelengths of light, including infrared and ultraviolet, that interact with the physical structure of the thread, not just its color.
Oh, wow.
It strips away the visual noise of the dye. To the AI under this light, a tiny knot of thread and net doesn't just look like a dark spot. It looks like a sudden, glaring mountain range rising up from a perfectly flat plain.
That is incredible. So they create this hyper-controlled, perfect baseline of light, and because the AI is bolted directly to the loom, it can detect that mountain range in under 100 milliseconds.
Precisely. It sees the broken thread, instantly flags it, and sends an electrical pulse to cut the power to the loom, completely bypassing the cloud. The machine reacts at the speed of the physical material.
It's just phenomenal.
Yeah.
But here's where it gets really interesting, because this incredible sub-100 millisecond speed on the manufacturing side is actually being perfectly mirrored by a speed revolution happening long before the loom even turns on the design side.
Right, the prototyping phase.
Yeah, and this is where CAD, computer-aided design, enters the picture. The IJSAT academic paper details how CAD is eliminating massive bottlenecks in the prototyping phase.
Because before you can weave 200 meters a minute, you have to know exactly what you are weaving. And historically, the design phase was agonizingly slow.
The paper actually broke down the pre-CAD workflow, and it blew my mind.
It's so manual.
It is. If a brand in New York wanted a new plaid fabric for a fall collection, a designer would literally sketch the weave structure on graph paper. Then a specialized painter in a studio would use tiny brushes to paint a physical copy of the design on a piece of hardwood to ensure the colors were completely opaque and accurate.
Hardwood. Think about that.
Right. And then they would mail that wooden board to the mill in India. The mill would manually set up a sample loom, weave a physical prototype, package it, and airmail it back to New York.
Taking weeks.
Weeks. And if the client looked at it and said, can we make the red stripe a little darker? The entire physical loop started completely over. It took weeks, sometimes months, just to agree on a single fabric.
It was an incredible waste of raw materials, shipping fuel, and human time.
Completely.
Today, CAD entirely eradicates that physical prototyping loop. But it's important to understand how the software actually replaces physical reality. It isn't just Photoshop.
It's deeper than that.
Much deeper. Modern textile CAD uses advanced physics engines.
Like the physics engines in a video game.
Exactly like that, but often much more precise. The CAD software calculates the specific friction coefficient of the raw fibers, the tension of the yarn twist, the weight of the dye, and gravity.
That is insane. It simulates the actual physics of the thread.
Yes. So when a designer alters the hue or adjusts the weave structure on their computer screen, the software doesn't just show them a flat picture. It simulates exactly how that specific blend of cotton and polyester will drape, shear, and fold over a 3D digital avatar.
So the designer's computer is now directly connected to the final manufacturing process. They run the simulation in New York, hit approve, and the digital file is sent instantly to the smart factory in Louisiana.
Right.
The Edge AI is calibrated to that exact digital file, and the loom starts reading it perfectly.
It is the complete digitization of the physical workflow.
If we step back for a second, solving this massive optical bottleneck on the factory floor and eliminating months of prototyping with CAD, it doesn't just save time and money. According to our sources, it fundamentally shifts the human toll and the environmental footprint of the entire textile industry.
It has a profound impact.
And this brings us to a concept I absolutely loved in The Quiet Architect: restorative engineering.
Yes. It's a profound, almost philosophical shift in how we talk about the purpose of automation and technology in the workforce.
It really is, because the narrative we are fed every single day is that AI is a disruptor. It's coming to replace human workers, to automate away middle-class jobs, and to maximize corporate profits by gutting the working class.
That's the common fear.
But the author of this manifesto totally flips that script. They enthusiastically argue that the goal of engineering shouldn't be disruption at all, it should be restorative.
And the author grounds this philosophy in a very intense, high-stakes personal anecdote.
Yeah, this part was wild.
Before they ever stepped foot in a textile mill, they built robotic systems specifically. 6-axis Techman cobots integrated with advanced vision systems for handling live, volatile munitions.
And grenades.
Literally hand grenades. They were watching factory workers handle live explosives on a chaotic assembly line. These workers were essentially holding their breath for 8 hours a day, terrified that a single slip of the fingers or a momentary lapse in concentration would cost them their lives.
The quote from the author really stuck with me here. They wrote, "It wasn't innovation that moved me to automate that line, it was fear. I built a process around a robotic arm to give them safety, not headlines."
And that is the beating heart of restorative engineering. The technology is not deployed to replace the human. It is deployed to restore their safety, their sanity, and their dignity.
Wow.
When you take that exact same philosophy and apply it to the textile industry, the Edge AI bolted to the loom acts in the exact same way. The author calls it an optical relief system.
Optical relief. I love that. You aren't taking away a job, you're taking away a biological torture device.
Precisely. You are removing a human worker from a visually exhausting, physically debilitating task, staring at a 200-meter-a-minute blur until their eyes cross and their head pounds, and you are elevating them.
You're giving them their eyes back.
Yes. You are restoring their vision, relieving their physical strain, and promoting them from a manual inspector who is set up to fail to a machine supervisor who is set up to succeed. The human is still fundamentally necessary on the floor, but they are managing the intelligence of the system, optimizing the workflows, and maintaining the hardware rather than being ground down by the sheer friction of the machine.
So what does this all mean for the broader global impact, specifically the environment? Because we hear the word sustainability thrown around by literally every fast fashion brand on earth right now, usually accompanied by pictures of green leaves and bamboos.
Well, this is where we have to separate marketing from mechanics. True sustainability isn't just a PR campaign about launching a small line of organic cotton shirts while churning out millions of polyester ones. True sustainability is mathematical.
Okay.
It is simply not weaving the wrong fabric in the first place.
Okay, let's look at the numbers then. How much waste is this AI actually stopping?
The industry news reports we reviewed are very clear on this. AI-driven textile automation cuts raw material waste by 15 to 20% immediately.
20%.
Yes. Think about the baseline we established earlier. Human inspectors miss so many defects that a factory runs an 8 to 12% defect rate. When you bolt that edge AI camera over the loom, running at sub 100 millisecond reaction speeds, it catches the microscopic knot, stops the machine, and allows a human to fix the thread before the fabric is woven.
So it prevents the error from becoming yardage.
Right. It drives the factory's defect rate down from 12% to a highly controlled, predictable 2 to 4%.
So you are instantly reclaiming up to 15% of your raw cotton, your electricity, your labor hours, and the thousands of gallons of water used in the dyeing process simply by catching mistakes the exact millisecond they happen.
Exactly.
That isn't carbon offsetting. That is real, measurable waste prevention at the source.
It is. But the sources are quick to point out that this waste reduction isn't just happening at the end of the loom. It is happening across the entire life cycle, driven by data. The IJSAT study talks extensively about the implementation of digital twins.
I've heard this term in aerospace, but how does it work in a garment factory?
A digital twin is exactly what it sounds like, a complete living virtual replica of the actual physical production system. The factory installs thousands of tiny IoT, Internet of Things, sensors on the legacy iron.
Right.
These sensors measure heat, vibration, humidity, and motor torque. All that data feeds in real time into the 3D computer model.
So the computer knows exactly what the physical factory is feeling.
Exactly. And because the computer knows the physics, it can run simulations into the future, it can identify inefficiencies, and more importantly, it can predict equipment failures before they happen in reality.
Give me an example of that.
Sure. If a digital twin simulates that a specific bearing on Loom 4 is vibrating at a frequency that indicates it will shatter in 3 days, the maintenance team replaces it during scheduled downtime today.
Which prevents a catastrophic machine breakdown that would have ruined hundreds of meters of fabric in stalled production. The study notes that integrating these digital twins cuts operational costs by up to 30%, largely by eliminating the chaos of unplanned downtime and trial and error manufacturing.
And that digital simulation extends all the way to the consumer. The industry reports highlight the rise of AI-driven 3D garment visualization and virtual try-on, or VTON, technology.
Which solves a massive environmental problem in e-commerce.
It really does.
Because right now, the consumer behavior is to order 3 sizes of the same pair of pants, try them all on at home, and mail 2 back.
The bracket shopping method.
Yeah, exactly. And we all know that a massive percentage of returned fast fashion doesn't get restocked. It goes straight into a landfill or an incinerator because the logistics of inspecting, repacking, and restocking a cheap garment cost more than just throwing it away.
It's an ecological disaster driven by consumer convenience. But with Viaton, consumers can use their smartphone cameras to create a hyper-accurate 3D avatar of their own body. Because the CAD files used to design the clothes have actual physics data built into them, they know the weight and stretch of the denim. The Viaton software can accurately show the consumer exactly where the pants will be tight, how they will fold at the knee, and where they will drape.
So you drastically reduce the e-commerce return rates because people actually know how the clothes will fit before they hit buy. By shifting the trial and error phase of both manufacturing and shopping entirely into the digital realm, you aggressively slash the amount of physical fabric that ends up in a landfill.
Beyond the digital optimization, it's also worth noting the advancements in physical chemistry that the IJSAT paper brings up. We're seeing nanotechnology applied at the molecular level of the fibers.
Nanotech and clothes.
Yeah. By altering the surface energy of the threads, engineers are creating fabrics with microscopic peaks that suspend water and dirt, making them inherently self-cleaning or water-resistant.
Oh, wow.
These advanced materials require significantly less hot water and detergent over their life cycle, rendering them exponentially more sustainable. We are also seeing the adoption of eco-friendly dyeing methods that utilize less water and drastically reduce the toxic chemical runoff that has historically devastated the local ecosystems around textile manufacturing hubs.
So if you are a CEO or a leader in a major textile company right now, what is the core strategic takeaway from all of this?
The core leadership insight from every source we reviewed is that the era of treating sustainability and profitability as competing metrics is over. They are now the exact same mathematical metric.
Okay, I have to push back a little here. Going green has always been expensive. It's always been a PR write-off or a premium product line. How are they the same metric?
Because the mechanism of going green has changed. Historically, sustainability meant buying expensive organic materials and accepting lower margins. Today, sustainability means reducing your defect rate through Edge AI, which saves you millions of dollars in wasted raw materials and energy.
Right.
That is pure profit added directly to your bottom line while simultaneously, organically lowering your carbon footprint and water usage.
Oh, I see. The efficiency is the sustainability.
Exactly. Furthermore, the global market is forcing this alignment. Massive Western retail brands are under immense regulatory pressure from governments and social pressure from consumers to clean up their supply chains.
They have to answer for where their stuff comes from.
They do. They simply will not sign contracts with dirty, inefficient factories anymore. Precision AI is rapidly becoming the only way a factory can achieve both the massive volume required to keep their unit economics down and the verifiable green credentials required to even get a seat at the table with a major buyer.
Okay, so the Edge AI catches the physical defects on the loom. The CAD and the digital twins ensure we design the fabric perfectly in the virtual world with minimal waste. The physical manufacturing is totally optimized. But here's where it gets really interesting and where I have to admit I get pretty skeptical. In a totally fragmented, globalized supply chain, where cotton is grown in one country, spun in another, woven in a third, and sold in a fourth, how does a brand sitting in an office in New York actually prove to a consumer in London that a garment made in Louisiana was manufactured ethically?
It's the multi-million-dollar question.
Right, because anyone can just slap a cute green leaf logo on a cardboard tag and call it eco-friendly. How do we actually know?
And your skepticism is entirely justified. Greenwashing is rampant, which is exactly why the industry is turning to what the sources call the trust protocol. Enter blockchain.
Okay, stop right there. Whenever someone says the word blockchain, I know half the audience instantly rolls their eyes, thinking about volatile cryptocurrencies, tech bros hyping up coins, and pictures of bored apes. We need to separate the hype from the hardware.
We absolutely do. We need to strip away all the crypto speculation.
Huh.
In the context of global industrial supply chains, blockchain has nothing to do with digital money.
Okay, then what is it?
It is simply a rigid, unchangeable, decentralized digital ledger. It is a permanent mathematical record of transactions for the physical world.
So how does a digital ledger actually build trust for a physical t-shirt?
It provides total, verifiable transparency and traceability from the moment the raw fiber is harvested all the way to the retail shelf. Think of it as a digital passport for the fabric.
A passport? I like that.
When a specific bale of organic cotton is harvested, that event, the location, and the farmer's credentials are cryptographically hashed and logged on the blockchain. When that cotton is spun into yarn, dyed using verified eco-friendly chemicals, and woven on a loom monitored by our Edge AI, every single step generates time-stamped data.
And that data goes onto the ledger,
That data is immutably recorded on the ledger.
meaning it literally cannot be altered, edited, or faked after the fact by a middleman trying to cut corners.
Exactly. This allows fashion brands to thwart counterfeiting because a fake shirt won't have the digital history. It allows them to definitively verify their sustainability assertions and prove their fair trade certifications. In theory, the consumer can walk into a store, scan a QR code on the tag, and see the entire, unalterable history of the garment they are holding.
Okay, I hear that. It sounds brilliant in a boardroom presentation. But I have to push back here. Hard. Let's look at the real world. The IJSAT study explicitly mentions the absolute economic dominance of the fast fashion model.
True.
Do average consumers actually care about a cryptographic blockchain ledger when they're standing in a store on a Friday night just looking for a cheap, trendy t-shirt to wear for the weekend? Isn't speed and rock bottom cost still the absolute only thing driving consumer behavior?
What's fascinating here is that you are entirely right about consumer psychology. Most people buying a $5 t-shirt do not care about the blockchain, but you are looking at blockchain from the wrong angle.
Oh.
The true power of this technology in textiles isn't consumer-facing marketing at all. It is deeply, fundamentally operational. It's B2B, business to business.
If the consumer isn't looking at it, who is?
The buyers, the suppliers, and the auditors. And they are interacting with it through smart contracts.
Okay, explain a smart contract to me. How does code execute a business deal?
A smart contract is self-executing code living on the blockchain. The terms of the agreement between buyer and seller are written directly into lines of code. Imagine a massive fabric producer in Louisiana and a retail buyer in London. Usually this involves endless invoices, letters of credit, quality disputes, and weeks of waiting for international bank transfers.
A ton of paperwork.
Right. Using a smart contract, they automate the entire relationship. And this is where the edge AI we talked about earlier becomes crucial. The edge AI camera on the loom acts as what blockchain engineers call an oracle, a physical truth teller for the digital ledger.
Ah, so it bridges the physical and the digital.
Exactly. The buyer writes a smart contract that says, I will pay $100,000 for 10,000 meters of fabric, but only if the defect rate is under 2%.
Okay.
The loom runs. The edge camera monitors the fabric in real time. The moment the camera digitally logs the 10,000th meter and cryptographically signs a certificate stating the defect rate was 1.8%, it pushes that data hash to the blockchain.
And the contract sees that.
The smart contract sees that the physical condition has been met and instantly, autonomously triggers the bank API to release the funds to the factory in Ludhiana.
Oh, wow. So it completely eliminates the middlemen. There are no invoicing delays, no lawyers arguing over quality standards, no 90-day waiting periods for the factory to get paid. The machine verifies its own work and gets paid by a robot.
Precisely. It minimizes human fraud and vastly improves B2B operational efficiency. It provides massive cash flow relief to the factory.
It's huge for them.
And regarding your point about fast fashion blockchain forces that hyperspeed model to become accountable, right now the fast fashion model thrives financially by externalizing its true costs hidden over production, toxic environmental dumping, and poor labor conditions at subcontractors.
Out of sight, out of mind.
Blockchain directly tracks those hidden realities. When supply chains are forcibly made transparent through digital ledgers, large Western brands can no longer claim plausible deniability about the actions of their Tier 3 suppliers.
Okay, but a smart contract doesn't physically load the fabric onto a shipping container. How do we know the physical fabric matching the ledger is what actually arrived in London? Couldn't they just bait and switch the fabric after the AI inspects it?
That is the ultimate vulnerability, the last mile problem of blockchain. To solve it, factories are starting to weave microscopic, physical tracers directly into the edge of the fabric itself.
Physical tracers.
These can be UV reactive threads or even synthetic DNA markers that are linked to the digital hash. If customs or the buyer audits the shipment, they scan the physical fabric, and if the physical tracer doesn't match the digital blockchain record, the smart contract flags it as fraud.
That is brilliant. So the pressure to adopt this isn't coming from the teenager buying the shirt. It's coming from international trade regulators, ESG investors, and the massive brands trying to protect their market cap from a PR disaster.
Exactly. It is systemic, structural accountability driven by unchangeable mathematics.
Okay, so we've laid out this incredible vision. If all of this technology, the sub-100 millisecond edge AI catching defects, the digital twins optimizing the maintenance, the CAD systems eliminating months of physical samples, and the blockchain securing the global contracts, if this is also revolutionary, so efficient, and so profitable, the most obvious question in the world is, why isn't every single factory in India, Bangladesh, and Vietnam using it tomorrow? What is the holdup?
The answer lies in a really complex, messy mix of harsh financial realities on the ground and deeply ingrained human psychology. The final major theme from our sources focuses on this massive investment hurdle.
Right, because the IJSET study didn't just look at high-tech labs. They specifically went into traditional manufacturers in Ludhiana, and the picture they painted was not one of effortless, enthusiastic tech adoption.
Not at all. The primary towering barrier is the MSME financial trap. MSME stands for micro, small, and medium enterprises.
Okay.
We often think of manufacturing as massive multinational conglomerates, but MSMEs actually make up the vast majority of the textile sector in emerging markets like India.
Interesting. I didn't realize they were the majority.
They are. You have to remember the economic context we established earlier. These factories are operating on razor-thin margins. They are fighting for fractions of a penny per meter. You simply cannot walk into an Indian textile factory, point to a perfectly functional, albeit 50-year-old loom, and ask the owner to throw it in the trash and buy a brand new $50,000 piece of Industry 4.0 smart equipment.
They just don't have the cash.
They have massive capital constraints. They cannot get the loans.
Not to mention the infrastructure. The industry report notes that reliable internet connectivity and a stable power supply are still major daily issues in some of these industrial hubs.
Exactly. You can't run a hypersensitive smart factory if the municipal power grid fluctuates and drops every afternoon. So, for a factory owner, there is a massive upfront capital expenditure capex to not just buy the shiny new AI camera, but to upgrade the basic facility infrastructure, the wiring, the routers, and the servers just to support it. It's a non-starter.
But the tech industry isn't just giving up, right?
Right.
Because they know the market is huge.
Yeah.
I was totally fascinated by the bootstrapping solution outlined in The Quiet Architect. It's a brilliant business pivot. The author argues that tech vendors need to completely stop trying to sell expensive AI hardware to these factories.
Yes. They realize that asking a factory to take on CapEx risk is a losing battle. So instead of selling a piece of hardware, they shifted to a SaaS model for the physical world. They sell QA as a service, quality assurance as a service.
I want to break down how smart this is. The tech startup comes into the factory and provides the custom multispectral camera rig, the lighting, and the NVIDIA Jetson Edge computer at cost, or in many cases, completely for free.
Zero upfront cost.
And they literally bolt it right over the existing legacy iron of the old loom. The factory doesn't have to buy a new machine, they just make their dumb machines smart. And then, instead of a $50,000 invoice, the tech vendor simply charges the factory a fraction of a cent for every meter of flawless fabric that the AI successfully processes.
It is a masterclass in aligning incentives. It completely removes the capital expenditure risk for the factory owner. It turns a terrifying CapEx investment into a manageable, predictable OpEx operational expenditure.
Win-win.
Exactly. The tech vendor only makes money if their AI actually works and successfully reduces the factory scrap rate. If the AI hallucinates, the tech founder loses money, not the mill owner. The factory gets world-class edge AI retrofitted onto their decades-old machines without having to beg a bank for a loan, and the tech vendor gets a highly lucrative, recurring revenue stream tied directly to the physical output of global manufacturing.
But even with clever, risk-free models like QA as service, upgrading an entire nation's industrial base requires broader financial support. And the sources point to some crucial macro-level interventions here.
Yes, the Indian government has recognized that if they want to reach their incredibly ambitious goal of boosting textile exports to $100 billion by 2030, they have to modernize the MSMEs. The global buyers demand it.
Because they have to step in.
So the articles highlight specific government schemes like the PLI, the Production-Linked Incentive Scheme, and TUFS, the Technology Upgradation Fund Scheme.
What do those acronyms actually do for a guy running a factory in Ludhiana?
They act as the financial bridge. They provide the necessary tax cuts, direct monetary grants, and heavily subsidized interest rates to lessen the financial strain of technology adoption.
Like a safety net.
If a factory owner wants to buy new automated looms or upgrade their facility's power grid to support digital twins, the government schemes absorb a significant percentage of that cost. They basically de-risk the macro investment, providing a financial safety net, while these traditional hubs upgrade their infrastructure to compete with heavily automated facilities in China or Vietnam.
Okay, so the money is one thing. You can solve the hardware cost with QA as a service, and you can solve the infrastructure cost with government grants. But the IGSAT study reveals a barrier that is so much harder to fix than money because it's rooted in human emotion, the cultural barrier.
The fear of obsolescence.
Yes, the academic researchers conducted in-depth face-to-face interviews with blue-collar garment workers and middle management in Ludhiana, and the workers were explicitly vocally resistant to the smart factory rollout.
People are afraid of what they don't understand.
There is one quote from the study that really stopped me in my tracks. A worker told the researchers, "We are very much comfortable working through traditional methods. We don't want to work on new technology. New technology will leave us jobless."
And we have to acknowledge that this is a completely rational, historically justified fear.
Oh, absolutely.
When a blue-collar worker hears the words automation and artificial intelligence, they don't hear a TED Talk about restorative engineering. They hear redundancy. They look at a multispectral camera doing the exact visual inspection they have done for 20 years, and they immediately logically assume they are going to be fired.
So how does management overcome that deeply entrenched resistance? Because if the workers fear the machine, they will sabotage it, ignore its alerts, or refuse to engage with the digital twin dashboards, and the whole multi-million-dollar smart factory concept completely collapses.
The IJSAT study outlines that management cannot just mandate the new tech from the top down. They have to actively foster a culture of innovation, and they have to put real money behind it. It requires heavy, sustained investment in upskilling and training.
Right. The study mentions specific training programs designed to transition these workers out of repetitive manual labor and into higher-level, multi-skilled positions.
And the absolute key to making that transition work is compensation.
You have to pay them for the new skills.
Exactly. One worker in the study noted a positive shift, saying, "The employer is giving us training to learn new methods and assured us that if we master this new technology, we will receive good compensation." You overcome the primal fear of joblessness by guaranteeing that operating the AI makes the worker more valuable to the company and therefore higher paid than they ever were when doing manual inspection.
It's about visibly moving them from physical laborers to digital operators.
And paying them for that new cognitive skill.
But there is a dark side to this choice, isn't there? For the factory owners who look at the training costs, the digital twins, the smart contracts, and decide it's all just too complicated, too expensive, or too culturally difficult. The ones who just want to stick to the traditional methods that worked for their grandfathers.
If we connect this to the bigger picture, the warning from the academic and industry sources is absolute. Factories that take a passive, wait-and-see approach are signing their own death warrants. The IJSAT study explicitly warns that they will become the Kodak or Nokia of textiles.
Ouch, that is a brutal historical comparison.
It is.
Kodak invented the digital camera and then buried it because they wanted to keep selling film until digital wiped them off the map.
It is brutal because it is exactly what is happening. The global market is completely unforgiving. If a factory in India refuses to digitize, they will lose ground rapidly to offshore competitors who are using edge AI to drop their defect rates to 2%, who are using CAD to approve designs in 24 hours, and who are utilizing blockchain to cryptographically prove their sustainability to demanding Western buyers.
It's a dabbed or die.
The survival mandate for the 21st century is clear: digitize your physical workflows, embrace the math, or become entirely obsolete.
Wow. Okay, let's pull all of these massive concepts together. We have taken an incredible journey today through the hidden architecture of an industry that most people barely give a second thought to when they get dressed in the morning.
It's a lot to process.
It really is.
Yeah.
We started by stepping onto the factory floor and looking at the violent, terrifying reality of a power loom pushing fabric at 200 meters per minute. We saw how human optical fatigue was physically incapable of keeping up, bleeding massive revenue through microscopic defects.
And we saw how the tech industry's arrogant default answer, just send it to the cloud, completely failed, because a 500 millisecond latency is an eternity when a machine is moving 3 meters a second.
From there, we explored the actual mechanical solution, Edge AI. We saw engineers quantizing massive neural networks, bolting them directly onto legacy iron, and using the topographic mapping of multispectral light to catch microscopic flaws in under 100 milliseconds.
We saw how CAD physics engines have transformed months of wasteful physical prototyping into hours of precise digital simulation.
And we challenged the narrative of automation as a job killer, reframing it through the lens of restorative engineering. The profound idea that technology shouldn't just replace human workers, but elevate them, restoring their safety and dignity by taking them off tasks that biologically break them down, like staring at a high-speed loom or handling live munitions.
We connected that localized physical precision to the global demand for true sustainability. We saw how dropping defect rates to 2% and using digital twins to predict machine failures reclaims up to 15% of material waste instantly.
Proving that ecological responsibility and ruthless profitability are now the exact same metric.
And we looked at how blockchain acts as the global trust protocol, creating an unchangeable cryptographic ledger that forces the fast fashion model to be accountable while using smart contracts to automate international payments.
Finally, we faced the harsh economic realities of the MSME financial trap and how brilliant bootstrapping models like QA as a service, combined with aggressive worker upskilling, are the only ways to avoid becoming the next Kodak.
The overarching theme is that the invisible architecture of the clothing industry has been completely irreversibly rebuilt. It is no longer a traditional craft. It is an industry defined by extreme computational speed, restorative human engineering, mathematical waste reduction, and cryptographic trust.
So why does all this matter to you? Whether you are a supply chain executive trying to protect your margins in a volatile market, an AI developer looking to understand the real-world physical limits of software, or simply someone standing in a retail store deciding which new jacket to buy, you are an active participant in this massive, invisible, high-tech ecosystem. The muddy, chaotic waters of traditional manufacturing are being forcefully clarified by mathematics.
It is a profound, permanent shift from the limitations of the physical world to the optimization of the digital.
Which leaves me with one final kind of provocative thought for you to mull over as we wrap up.
Oh.
Right now, as we've discussed, we're using these incredible edge AI systems to master the physical tension of fabrics on the loom. We're using algorithms to analyze global social media to predict exact fashion trends, and we're using CAD to simulate how those clothes will drape. But if the machines are already inspecting the physical clothes, and the digital twins are simulating the exact production costs, and the AI is forecasting exactly what colors and cuts humans will want to buy how long, until the machines aren't just inspecting our clothes, but entirely dictating what we wear.
That is the ultimate question.
If the ultimate logic of the smart factory floor is all about supreme mathematical efficiency and absolute zero waste, will the future of human fashion be designed not by human artists in studios, but entirely by what is most mathematically efficient for a sub-100 millisecond edge AI to weave?
This raises an incredibly important question about where the line is drawn between algorithmic optimization and true human creation.
It really does. At the start of this deep dive, we talked about the naive expectation of software being this frictionless, clean utopia and how that collided with the brutal, messy reality of a physical loom. Well, the AI is mastering the physics of the loom. The software is winning the war on friction.
It certainly is.
The question is, when the smart factory is finally mathematically perfect, what kind of uniform will the machine decide we are allowed to wear? Think about that next time you pull a shirt over your head.